Shall we start?
Okay, sir.
Okay, right. So we'll just look at the same problem. Now this time 285 kilonewton meters. And if you find M over FCK BD squared, it's 0.23 greater than 0.167. That means we have to doubly reinforce it. And to find AS dash, we have to simply substitute in the equation. And 0.167 FCK is 25. Breadth of the section is 250. D is 445 squared. And the D dash value is 55 millimeters. So you can find the reinforcement required in compression. And this can be easily provided by using two numbers of 20 millimeter bars, each having 314 millimeters. So 628 millimeters squared. And then you can also find E dash over D ratio, which is 0.123 less than 0.171, which means we can actually use this equation. The reason is compression reinforcement would have yielded if the maximum moment is acting. Then you can simply substitute in this equation and find the tension reinforcement needed. And you can see 1765. Now we need 6 numbers of 20 millimeter bars, whereas earlier we had to use only 4 numbers of 20 millimeter bars. Now we have to go up to 6 numbers of 20 millimeter bars. Now we'll move to the next variation that you can think of, and that is the design of flange beam. Again, when you are dealing with foundations, we have to do flange beams. We come across flange beams, especially when you are dealing with inverted T-type foundations, and they are heavily loaded. So you have to be a little careful when you are designing the flange beams when they are heavily loaded. When they are lightly loaded, it's fairly straightforward, not a problem at all. But when the flange beams are heavily loaded, then we have to be a little careful. So we'll see why we have to be a little careful when the flange beams are heavily loaded. And especially when you are using inverted T-type foundations, you will come across that certain places it behaves as a flange beam, certain places it behaves as a rectangular beam. So whenever you do in situ cast construction, beam and slab cast together, the slab can contribute to carry the compression. Then the rectangular beam can be designed as a flange beam. So if it is a flange beam, and let's say that we know the width of the flange, and we also know the depth of the flange, HF, then the maximum, it's possible to have this as singly reinforced, where the neutral axis lies within the flange, and actually we are looking at this rectangular stress block lying within the flange. We are looking at the condition that the rectangular stress block lying within the flange. So the maximum force in concrete, the maximum force that this concrete can carry is the area of the flange multiplied by the maximum stress in concrete. And the lever arm corresponding to that is D minus HF over 2. So the maximum moment that this flange section can carry is equal to 0.567 FCK multiplied by the breadth of the flange, depth of the flange multiplied by Z value. The corresponding Z value is D minus HF over 2. So if the design moment is less than this, design the beam as for a singly reinforced beam. So when you have a flange beam, you can straight away find this value. And then if the moment to be carried is less than this, then you don't have to worry about anything. You can simply design the beam as a flange beam. And if the moment is greater than this, then what happens is the neutral axis can be somewhere here. The neutral axis can be somewhere here. And still it can be singly reinforced if XOD ratio is less than 0.45. If XOD ratio is less than 0.45, still it can be singly reinforced. So the moment carrying capacity of this situation and the situation where the neutral axis is this neutral axis is such that this section is fully utilized, will have only a very little difference in moment. We'll have a very little difference in moment. So if this 0.8 times x is greater than this, that means neutral axis is somewhere here. How do you find the moment carrying capacity of a flange beam? How do you find the moment carrying capacity of a flange beam? This can be still singly reinforced, but how do you find the maximum moment carrying capacity of a flange beam? What you have found here is not the maximum moment carrying capacity. This moment carrying capacity is the one corresponding to neutral, the neutral axis at a location, so that the full flange has been utilized. All concrete in the flange has been utilized. But there's another situation where the X over D is 0.45, and that is the maximum moment carrying capacity of the flange beam as singly reinforced. How to find that value? What we do is, first we will consider this flange beam as two beams. So what we do is, we consider the flange beam as two components. Flange beam is like this. We consider it consists of this component, and that is BF, BW, and we say the moment carrying capacity of the flange beam is D dash. Then we say M is equal to 0.567 FCK BF minus BW. That is the shaded portion. Multiplied by HF. So that is this area. So this is the area. This is the stress. Then D minus HF divided by 2. This is the lever arm. Plus the maximum moment carrying capacity of a rectangular section is given by 0.167 FCK B D square. So this is the maximum moment carrying capacity of a flange beam when it is behaving as singly reinforced. And if we have a moment greater than this, then we have to go for this situation where we provide extra reinforcement. We provide ACE dash and ACE dash. That means we doubly reinforce the flange beam. And when the flange beams are carrying very heavy moments, this might happen. So when you have a flange beam, you can simply check M as 0.567 FCK BF multiplied by HF multiplied by D minus HF divided by 2. That means the full flange is in compression. That is this case. And if you want to push it little further, you can consider this case. That will give the actual maximum. And if you want to push it even further, you can go for this case where we can consider that we are going to provide some reinforcement to carry compression as well. So these are the three situations that you get in a flange beam. So when you have a flange beam, when you calculate the reinforcement, the easiest thing is to find this value. Write this equation and find where you are. And if the moment that you have to carry is less than this value, then you can simply consider it as a rectangular beam, and the width of the flange is BF. And if you find this moment is not enough, then you can calculate this moment and then see whether it's enough. If the moment that is acting on the section is even greater than the expression given by this, then you have to consider the situation where the flange beam is doubly reinforced. The flange beam is doubly reinforced. So those are the three situations that you get in case of a flange beam. So you can have a situation where the maximum moment with the whole area of the flange in compression. That is given by this equation. And if the design moment is less than this, design the beam as for a singly reinforced beam of rectangular shape. If the design moment is greater than this, then the maximum moment that can be carried as singly reinforced is given by this expression that I have just shown you. In equation 242, the first term represents the moment that can be carried by flange with BF minus BW. Second term represents the maximum moment that can be carried by the rectangular section of with BW. And if the design moment MD acting on the section is greater than the value given by 242, it is necessary to provide compression reinforcement as well. This is not a usual case, but in the case of foundation, sometimes you find this is needed. The reason is foundations can be very heavily loaded. So this is an example. The characteristic material strength is FCK 500, FIK 500, FCK 225. And then we consider that determine M1 and M2, M1 and M2. And you can just substitute in these equations. 0.567, FCK is 25, width is 400, depth is 100, D is 350, and you can just substitute and get the answer. And this 170, M2 is 187. And as I explained you earlier, these two will not have a big difference, because in one case we consider this area as in compression. In the next situation, we consider a little more of this area also in compression. So the compression area increases only by a little margin. Because of that reason, these two values will be fairly close. And then if you consider this value, it consists of a moment of 85.1 carried by the flange and a moment of 102.3 carried by the web. So total of 187. So if the moment is 150, the moment is 150, that means it is less than this value. That means we can singly reinforce it. If the moment is less than 150, the reinforcement requirement is found as if for a rectangular section, and for a rectangular section, the width of the section is considered as the flange width. So width of the section is considered as the flange width, and it's less than 0.167, and you can find the value of Z, 307 millimeters, and the area of reinforcement can be found. So if the moment is 180, which is in between these two, then the reinforcement is found considering that this 85.1 kilonewton meters can be carried by using the flange action. You considering the flange, and the remaining part of the moment has to be carried by the rectangular section. So what we do is, if the moment is 180, then first we'll remove this one, 85.1, and then the remaining moment has to be carried by the rectangular section. So 94.9 has to be carried by the rectangular section. So that can be, and the reinforcement needed to carry that can be determined by finding the M over BD, FCK BD squared. And you have to find the distance to the neutral axis. And with that, you can find the reinforcement required to carry a moment of 94.9. And also we can also calculate the reinforcement that is needed to carry a moment of 85.1, because we know the lever arm. So we need 652 millimeters square to carry 85.1 using the flange area, and by considering the rectangular area, we need 744. We need a total of 1,396 millimeters squared, and you can see it's greater than what we needed here, 1123. So to carry a moment of 150, we need 1123, and 180 is in between these two values that we calculated, which means the flange is fully utilized and part of the web is also utilized, not fully. So we have to consider that the beam consists of part flange, part web, and the flange part, we know all the details because we know it's fully in compression. But for the rectangular section, we do not know the exact neutral axis and the exact lever arm. So to find the lever arm for the rectangular section, we consider it as a rectangular beam carrying the remaining portion of the moment, which is 94.1. And that way we can actually determine the total amount of reinforcement needed. So is this clear? What happens when the bending moment is 180 kilonewton meters? So when the bending moment is 150, no problem, because it is less than the moment that can be carried by utilizing the flange fully. This is not a problem at all. Is that right? Can you give some feedback, please? And can you understand this one? Yes or no? Shamil, are you there? Shamil?
Yes, sir.
Are you there? You can understand this, no problem.
Uh, yes, sir. I understand the concept.
Yeah. Okay. So no questions. Dasun?
Hello, sir.
Darshan. Das.
Hello.
Yeah. Can you understand this, Dasun?
Yeah. Okay.
Okay, right. So if the moment is more than 180, so what is the value? 100. If the moment is more than 187, even for the flange section, we have to provide extra reinforcement. So if the moment is 210, then whatever the moment in excess of 187 has to be carried by the compression reinforcement. So the remaining moment is this 210 minus 187.4, 22.6 kilonewton meters has to be carried with the compression reinforcement with a lever arm of D minus D dash. So D dash is considered as 50 millimeters and D is considered as 350 millimeters. So then we can write the equation. This extra moment of 22.6 is given by 0.87 Fy, that is the stress in steel, multiplied by As dash multiplied by D minus D dash. So 22.6 is equal to 0.87 Fy As dash multiplied by Z. There should be Z here. And the value of Z is actually 500 millimeters. Oh, sorry, that is Z is take the value 22.6 multiplied by 10 to the power 6 divided by 0.87 divided by 500 divided by 300. There's something wrong in the equation. Here we should get D minus D dash, is right? Yes. Compression D dash is 50. D is 350. So this equation is here we get D minus D dash as well. And that is multiplied by 300. So the answer is 22.6 to the power 6 divided by 0.87 divided by 500 divided by 300. Answer is 173, not 152. Answer is 173 millimeter squared. So you might have to provide some extra reinforcement like 16 millimeter bars, two numbers of 16 millimeter bars, because we can't provide only one 16. So we might have to provide something like two numbers of 16 millimeter bars. And A splash is the total reinforcement. And that 73 has to be added to that. This moment, right. So I have corrected the note. So there's a correction. This is not 152, this is 179, because d minus d dash is missing here. So it should come here as 300. And then you get the answer as 173. And this also should be 173 millimeters square. So basically, this shows different variations that you can get in the design of a beam. It can be singly reinforced, doubly reinforced, or flange section. Even in the flange section, you can have one situation where the full flange is utilized, and the next situation is the maximum moment that can be carried as singly reinforced. The next situation is the moments are so high that even in the flange section, we need extra reinforcement. So when you have a flange beam, the easiest thing to do is to calculate the maximum moment that can be carried when the flange is fully utilized. And that will give you an idea whether the moment that you are dealing is excessive or not. If the moment is large, then you have to calculate the maximum moment that it can be carried. And then the extra reinforcement needed can be easily found. So the total amount of reinforcement that you need is for this particular case is the total reinforcement that you need to carry the maximum moment as singly reinforced plus 173 millimeters square. So that is so I have covered few examples. And the next thing that we have to do is design for shear. So once you complete the design for flexure, we have to design for shear. And in the method used in Eurocode is slightly different for shear, because it is considered something called variable strut inclination method. For shear designs, what we use is a method called variable strut inclination method. Because if you look at British code, they have used the inclination of the shear crack is at 45 degrees, whereas the actual inclination of a shear crack would generally be at around 30 degrees. So because of that reason, the Eurocode allow us to consider that the shear crack can occur with an angle of 22 to 45 degrees. And then we have to actually do the design in a slightly different manner. So there are various parameters we have to look for. And also we have to look for the minimum amount of reinforcement that is needed. So shall we cover shear from next day onwards? And if you have any question from today's lecture, you can ask. And otherwise, we'll cover shear in great detail next week onwards. And because I made a small correction for the note, I will upload the corrected note to Moodle. So you can download the latest version once I upload it. And what actually happens is in Eurocode, we consider that this angle is a variable. So it can vary between 22 to 45 degrees. And then there are quite a few equations and a little bit of checks to be made for shear. And then we'll cover an example as well that will help us to understand few other things like, calculating the effective flange width and so on. So shall we continue next week? Shamil?
Okay, sir.
Okay, right. So we'll continue next week, right? And we keep Saturday.
So I have one question.
Yeah. Yes.
In example 2.3,
2.3, yeah.
there D dash OD is 0.123. Yes, here D over D dash is 0.123 below.
Yeah.
So next, another 2 rows below.
Yeah. This 0.123, yeah. Yes.
So usually the limiting value is 0.171.
Limiting is the maximum value. Because if D dash is higher, say D dash is 100, right? Let's say D
Yes.
dash is 100. So if D dash is 100, 100 divided by 445 is 0.224. So if D dash is big, then what happens is this. If D dash is big means we are moving this way. Is that right? So when you are moving this way, the strain will reduce. So if the strain goes below 0.00217, then the reinforcement will not yield. It will have a force, but the reinforcement will not yield. Right? If the reinforcement does not yield, then what happens is we'll be here. We'll be somewhere here. Then the force will not be 500 divided by 1.15. Then the force will not be 0.87 times Fy. We'll be somewhere here. So that's why we have to make sure that we remain somewhere here. We remain somewhere here. We remain more than 0.00217. So the way that we can remain there is to be somewhere here. If you are close to this, then we can remain close to 0.00217, no more. But when you are moving this way, then we are reducing. So that's why we have to get this D dash over D value. And so that's why when we calculate this, this example, if we are 55, okay. But if we are about 100, then we are above this. That means, then if we are greater than this, then we have violated this limit. Is that clear, Jamil?
Yes, sir. Okay.
Okay, right. Any other question like this? So in that case, we'll end the lecture and I will upload the new note after converting it to PDF, and we'll continue next time. And shall we keep Saturday afternoon free? Who is the bachelor? Indunil? Who is your batch rep? For 10 minutes?
Indonesian.
Right. He is not there today. Is it?
He's absent, I think.
Yeah. For the time, for tentatively, we'll keep Saturday afternoon free then, no? To continue this lecture. Okay, then in that case, I'll
Okay,
stop the lecture, right?